reasoning of Einstein. Bohr disagreed immediately, and well, it's embarrassing because they gave me a medal by the name of Niels Bohr. But I have to say that I spent tens, probably hundreds of hours reading Bohr. Bohr is really very obscure. To know what Bohr means demands a mind more smarter than mine, okay? And I have an anecdote with that. You know that Bohr developed the concept of complement. I have a former student, seen here, she's a Danish, so don't repeat it to the Danish people, okay? Yes, but Bohr was an adept of complementarity. He said, well, when you have a conceptual problem, think of complementarity. And once he said, truth and simplicity and clarity, truth and clarity are complementary variables, okay? And it's clear that Bohr wanted to be as true as possible. And so guess what is a clarity? A clarity is not so. So when you read Bohr, you do not know exactly why he disagreed with Einstein, but he had more or less the intuition. I think he's a genius. I'm laughing, but he's a genius. He had the intuition that if he would accept to complete quantum mechanics, then there would be a self-contradiction in quantum mechanics. He said that you cannot keep quantum mechanics self-consistent and accept to complete it. He could not demonstrate it, but in my feeling, from what I have read, he had the right intuition of something that would be demonstrated by Bell 30 years later. Okay, let us go to Bell. Before going to Bell, you have to understand that this debate between Bohr and Einstein basically did not interest anybody. There were old guys discussing, but there were plenty of young physicists using quantum mechanics every day and finding wonderful things with quantum mechanics, because quantum mechanics was extremely successful in understanding nature, structure of matter, etc. And even, well, this is a little not true literally, historically, but we all know that quantum mechanics has also allowed people to invent transistors, lasers, integrate circuits, etc. And a very important point is the following. There was no disagreement between Einstein and Bohr on the way to use the mathematics of quantum mechanics. The only disagreement was about interpretation. So people are using quantum mechanics, it works, they publish papers, they are promoted as professors, you know, etc., etc. And they know there is a debate between Einstein and Bohr, but they know that the debate is about interpretation, not about the way to use equation. And the people use equation every day, so they did not care. John Bell, in '64, thought again about this argument of Einstein-Polowski-Rosen and say, let us take seriously the conclusion of Einstein. Let us introduce the supplementary parameter, lambda, which tells us from the beginning that photon nu1 will go here and photon nu2 will be here. And it writes an extremely simple formalism. And if during the equation you ask me, I can demonstrate what I'm going to put here. This literally high school physics, okay, not more than high school algebra. You accept that you describe the result of a measurement here by a function that can take either value +1 or value -1, and this function depends on what? Depends on the property of the photon and on the orientation, okay? And similarly, you have a function capital B, which depends on the property of the photon and on the orientation, okay? And now you assume that these supplementary parameter lambda are distributed probabilistically according to a distribution function which is positive and normalized to 1 as any reasonable distribution of probability. From this, you can calculate the correlation coefficient between the result +1 or -1, and when you do that, so this is an example, the example of the simplest model you can think of, and you see you get the red curve, which is not bad because the quantum mechanical prediction is a blue curve. So with a very naive and very simple model in which you assume that you have rotational invariance and you say, okay, it's very simple. If the polarization is close to A, it's +1. If it is close to perpendicular to A, it's -1. And I put the frontier at 45 degrees. It makes sense. What simpler can you do? Okay? If I am close to the axis of polarizer, I get +1. If I am orthogonal, I get -1. I put a frontier in between. You get this result, which is very close to the prediction of quantum mechanics. So you may hope that going to your smart theory colleague, he knows all this special Bessel, Hankel function, all this stuff, you may hope that it will work. The discovery of Bell is that there is no way to find a model which will give the same result of quantum prediction for all values of the angle. So Bell theorem is it is impossible to have quantum prediction exactly reproduced at all orientation by any model à la Einstein. So this is how it works. It's really high school algebra to demonstrate that if you assume that the correlation coefficients are calculated with this idea of lambda, capital A, capital B, and rho, then there is a quantity which cannot be bigger than 2, cannot be less than -2, and this quantity takes 4 correlation coefficients calculated by having 2 orientations on the first side, A and A prime, B and B prime. So you calculate AB, AB prime, AB prime, etc. And you put a minus sign here. Why a minus sign? Well, I don't know. Bell was a genius. He had the right idea to put a minus sign, okay? And you find this again. High school algebra, you find that this quantity cannot be bigger than 2. On the other hand, remember the prediction of quantum mechanics. Take this set of angles. I have no time to elaborate because the chairman tells me he's going to kill me if I go beyond 1 hour and a half, and so I don't want to be longer than 1 hour and a half. Okay, and so thank you for the extra time. And so I have no time to elaborate, but you can easily you will have my transparency, or you buy my book, and transparency are for free. Okay? And then if you put the angles here, you have 1 over root 2, 1 over root 2, 1 over root 2, because you all know that cosine of 45 degrees is 1 over root 2. But look at A, B prime. A, B prime, you double, the cosine is negative. So it's minus 1 over root 2, but there is a minus sign. So it's again 1 over root 2, and the total is 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2, which goes to, students, 2 times root 2 equal 2.8, which is bigger than 2. So if we can describe the correlation by a model following the idea of Einstein, it cannot be bigger than 2, but quantum mechanics tells me for this set of angles, it has to be bigger than 2. So now we have a contradiction. This Bell theorem. The possibility to complete quantum mechanics according to Einstein's idea is no longer a matter of taste, no longer a matter of interpretation. It has turned into an experimental equation. We measure it, and either we find bigger than 2 or smaller than 2, and we decide. Okay. Before going to the experiments, I must of course discuss a little bit. Maybe there is a hidden hypothesis, maybe the reasoning is not good. Hundreds, thousands of physicists have tried to find bad hypotheses or bad reasoning in Bell's inequality. Nobody has found, and at the end of the day, the minimum hypotheses which are necessary for deriving something which is Bell's inequality or equivalent to Bell's inequality is the following. First, you insist on describing the correlation by introducing supplementary parameter lambda carried along by each particle. So they are produced together, then this particle goes with the lambda, and the other one goes with the same lambda, or at least it was initially the same. Maybe there is an evolution, but initially it was the same. The important point is this idea, carried along with each particle. So there is a property on this particle that will determine the outcome of the experiment. This is called local realism. These were the words of Einstein. You say that the particle which is here has a physical reality. The physical reality is the ensemble of the parameters that will determine the outcome of measurement. And this reality is local. It means that everything is here with the particle is not in a distant galaxy. Okay, that's the idea. So you insist on having a local realist view to derive Bell's inequality and find the contradiction. And secondly, there is a condition that Bell identified clearly in his paper. It's important for experiment. Bell said, the result of the measurement here should not be allowed to depend on the orientation of the other polarizer. If it would depend, you could not demonstrate Bell's inequality. And similarly, when you produce a pair, you should not be influenced by the direction that will be used later for the orientation of polarizer. So if you do a static experiment where nothing changes, then of course, when the photons are produced, they may be influenced by the orientation of the polarizer. So you will see that to fulfill this condition of Bell, one thing is to say that it is a reasonable hypothesis, but better if you could change the orientation of the polarizer while the photons are in flight. So during the flight of the photon, you change the orientation. Then, of course, the source cannot depend on the orientation because it's already emitted. But there is no time for a signal traveling not faster than light to go from here to there to influence the result here. So this is really a point which was clearly stated in Bell's paper. And so if you do an experiment like that, you have really a conflict between quantum mechanics and Einstein's worldview, which is local realism based on relativity. Okay? Okay. So what happened when Bell published this paper? 65, there were many, many experiments supporting quantum mechanics, but what happened is that when the paper was written, there was no experimental result available to test Bell's inequality. And the reason is that for most of the situations that exist in the world, where you have correlation, and you think that this correlation is very strong, anyway, usually they will not violate Bell's inequality, either because you can all interpret them from a classical point of view, and I could demonstrate that if you can interpret correlation from a classical point of view, there is no hope to violate Bell's inequality. But even in situations where people claim, oh, this is very quantum, actually, when you do the real calculation, you find that even the quantum calculation does not predict a violation of Bell's inequality. It's very rare that you predict a violation of Bell's inequality. So it was necessary to find a situation where the test is possible and to develop a specific experiment. And it was the beauty of a proposal by Clauser, Horn, Shimoni, and Hall in 1969 to make a practical proposal to do an experiment. And so this led to the first series of experiments. I call them the heroic pioneers, okay? In Berkeley, in Harvard, in '72, there was an experiment in Berkeley which agreed with quantum mechanics, and an experiment in Harvard which disagreed with quantum mechanics. It was interesting. You know, there is a big fight between the West Coast and East Coast in the United States, and they found opposite result. And a few years later, in Texas, agriculture and mining were, okay? They were in the middle, no, agriculture and mechanics, but it did not say quantum mechanics, agriculture and mechanics. But in Fry, in Texas, in '76, did an experiment which also supported quantum mechanics. There was a clear trend in favor of quantum mechanics, but all these experiments were quite far from the ideal scheme I have presented. This is why I embarked in '74, '75, in a series of new experiments where the goal to have experiment much closer to the ideal scheme on which the theoretical discussion goes, and I will present them. So we did that, and these experiments were completed in '82, and then I could get a PhD, which was good. Okay. And I will show you. We are the source of entangled photon of unprecedented efficiency, schemes closer and closer to the ideal Gedanken experiment, including the last scheme of quantum non-locality by using relativistic separation between the polarizer. And then, by the end of the '80s, there was the development of a third generation of experiments using a nonlinear effect, and there is a whole series of labs now having wonderful new sources of entangled pair. My source was much better than the previous one, but this one is much better than mine, and closing the glass loophole, etc., etc. Okay. So just to give you a flavor, how did we produce entangled photon? We excite an atom to an upper state which has the same parity as the lower state. So this was brand new at that time, 2-photon absorption. It was one of the very first experiments with 2-photon absorption. Why 2-photon absorption? The two levels have the same parity. You cannot directly absorb a photon between two levels which have the same parity because the dipolar operator is odd, etc. Well, anyway. But by adding 2 photons, you can excite this source, and this was for the first time. And when the atom is here, the only thing it can do is to deliver the pair of photons you were expecting, and by looking at the Zeeman structure of the intermediate level, you find that the atom is exactly delivering the entangled state you dream of, provided that you observe on opposite directions. And just to give you an idea, in the first experiment of 72, people had to accumulate data for hours and days and weeks. Here, at the end, everything being taken into account, we could get 100 real coincidences per second. You may not be impressed, but it means that in only 100 seconds, less than 2 minutes, you get 10 to the 4th, which means a statistical accuracy of 1%. A statistical accuracy in 1% in 2 minutes is much better. I can tell you, if you are an experimentalist, that a statistical accuracy in 1% in 1 week. Because to keep an experiment running stable for 1 week is a nightmare. To have an experiment working stable for 2 minutes, it's okay. We can do it. So it was fantastic. The first new experiment that we did compared to our colleagues of the heroic pioneers is that there were people who say, okay, entanglement is a property of the microscopic world. Or we say, what means microscopic? Well, when it becomes big, entanglement disappears. Say, what is a scale? So the guy would scratch their head and say, coherence length of the photon. Very good. My photon has a coherence length of 1.5 meters. So I pulled the polarizer at 6 meters, okay, entanglement was still there. Violation of Bell's inequality was still there. Okay. Now, first experiment very close to the ideal scheme. It's exactly what I presented. We could develop, it was brand new at that time, young people are going to laugh. They can buy flat for $10 on a catalog, okay? But at that time it did not exist. Beam splitters, polarizing beam splitter. A beam splitter that let one polarization go and the orthogonal polarization being reflected. Before, you had only a polarizer like a Polaroid, transmitting a polarization and absorbing the orthogonal one. So you don't get the result -1. And so you have to make plenty of calibration to figure out what would be result -1 if it would exist. When you have a scheme like that, and this for my friends, experimentalists, you do a single run. You have a 4-fold coincidence system. During that run, you get n plus plus, n plus minus, n minus plus, n minus minus. And then it's a self-calibrating experiment. The coefficient of correlation is the sum with the minus sign here divided by the full sum. It's self-calibrating. It's a wonder. For an experimentalist, when you don't need any extra calibration, it's wonderful. With this, look at the result. There is a quantity S predicted by quantity S that we measure. The green curve is a prediction by quantum mechanics taking into account the slight inefficiency of the experiment. The limit of +2 and -2 is here, and you see that we violate, that all the measured points exactly go on the curve predicted by quantum mechanics, and here at 22.5 degrees or at 67.5 degrees, we have a maximum violation of Bell's inequality, violation by more than 40 standard deviation. Remember that they gave the Nobel Prize for the Higgs for less than 5 standard deviation. So 40 standard deviation, you are safe, you can sleep. Nobody is going to argue that it is not convincing. But this also shows something. There was an experiment which had been done years before with an entangled state with gamma photon produced in annihilation of positronium. It was before the time of Bell's inequality. It was a very difficult experiment. So what have they done? You look for the correlation in polarization. You cannot afford to do many measurements because it takes forever, and you know the accelerator, you have only a few hours on it, etc. What have they done? Parallel, perpendicular, and 45 degrees. And at the end, go out, next experiment occur. And so 0 degree, there is no violation predicted. 45 degrees, no violation predicted. 90 degrees. This is just show you that in most situations, even when quantum mechanics is at work, it's very rare that you are in a situation where you predict a violation of Bell's inequality. And so if you don't know Bell's inequality, you don't know that the most interesting point is this one and this one. Okay. Last experiment. How am I doing this time? 20 minutes left? Good. I'm doing my best. Last experiment. We would like to switch this polarizer while the photon is in flight. As I told you, I could pull my polarizer until 6 or 7 meters. Okay, the room was like 15 meters long. Okay, light takes 20 nanoseconds to go from here, and I want to turn that in less than 20 nanoseconds. And you know the system, well, it's not very good, but the system is a polarizer, photomultiplier, another photomultiplier, but because we don't have to, we don't want to have the cosmic ray exciting the polarizer, we have a shielding in lead, a shield in copper, etc. So it's about 50 kilograms. You're not going to turn a piece of 50 kilograms in 20 nanoseconds, okay? So what we did is the following. We developed a switch which is based on an acousto-optic interaction between light and acoustic wave. I ordered one from a company. The company could never deliver. So finally I went into books and I discovered that water is, the company could not deliver because I needed a big system, and when they were trying to stick the transducer on the crystal, it would break all the time. So I discovered that water, this is for the young student. When a company cannot deliver, be smart, okay? Or you don't have the money to order, be smart. So I went to the book and I found that water is a very good acousto-optic medium. So I just put two transducers facing each other. I create my standing wave and it worked. So this is the system. This is a system that I built. So now it's a cube. I have one transducer, another transducer, only water in it, and it worked. So the idea is I have here now a switch which is able to either send the photon here or send the photon there. Here it's an orientation A, here an orientation A prime. I can switch every 10 nanoseconds. So every 10 nanoseconds, it's just like a polarizer switching from A to A prime, back to A, back to A prime. Same on the other side, okay? So I can switch every 10 nanoseconds, takes 40 nanoseconds to go from one to the other, and 20 nanoseconds, clearly I'm switching while the photons are in flight. So this, the system, okay? It was a difficult experiment because I had to put a diaphragm on the beam, so rather than a few minutes, it was a few hours. I have to insist that switching is not fully random because it's standing waves, but we are not stupid. We do not take good generator, so it is drifting. There is another one which is also drifting, so there is no correlation between the switching. But anyway, it's not fully random, okay? Well, I have to say that. And we got a convincing result. We got a violation by 6 standard deviation, and for the first time, it was tested with really a space-like separation. I mean, it was impossible to have any signal connecting the both ends of the experiment, or the signal has to go faster than light. Okay. Now, third generation experiments. Entangled photon produced by parametric down conversion. I have no time to tell you the details. It's nonlinear optics. By the way, there is a chapter on nonlinear optics in my book, okay, so you can also learn that. And with this system, the big advantage is the following. In my source, photons were going in any direction of space. In nonlinear optics, for people who know, you know that there is a so-called phase matching condition. And this phase matching condition convinces the photon to go into a well-defined direction. So the photon can be introduced into an optical fiber. And now you can stretch optical fiber for hundreds of meters, tens of kilometers. Nicolas Gisèle in Geneva is using the optical fiber of the telecom network, And he has tens of kilometers between the source and the detecting station, and he can still check Bell's inequality. Zeilinger, when he was in Innsbruck in '98, did an experiment where he stretched the optical fiber under a tunnel under the airport or something like that. And he did an experiment which was beautiful. I insisted that it was the first time my experiment switching polarizer was repeated. I told you that in my case it was periodic. But in the case of Zeilinger, the distance was long enough that he could make the decision locally with a random number generator. And it pompously, it's called a quantum random number generator, but whatever. But that means that when the photon is launched, then you make the decision of the orientation. So, and it's random, it's no longer periodic. So it's even better than the, but okay, it was 16 years later, so it's better to improve things. You better improve things if you repeat an experiment 16 years later. Okay. The result is that there are many experiments, there is a question of loopholes, closing loopholes, etc. If you ask me a question, I can go into details. But at the end of the day, everybody agrees that Bell's inequality have been violated consistently, that it is convincing. So it means that Einstein's local realism worldview is untenable. What does it mean? Einstein himself told us. You are going to tell me Einstein did not believe what he said? Yes, he believed in what he said. But in order to convince us, he told us, reasoning ad absurdum. If I was not right, this is what would happen. What would happen? This is written by Einstein. If we could not complete quantum mechanics according to my reasoning, we would have either to drop the need of independence of the physical realities present in different parts of space, I will comment, or to accept that the measurement of the first system changes instantaneously. This is a word of Einstein. It's between brackets, but it's Einstein, right? That the real situation of the other one. So what Einstein tells us, if I was not right, it would mean that the properties of the system which is here and the property of the system which is here are not independent of each other, in the sense that when I do something here, it could instantaneously change the situation of the other one. Of course, Einstein could not accept that, so he concluded that his reasoning was correct. But nowadays, we know that this reasoning is not correct, so we have to accept something like that. So some people call that quantum non-locality, the fact that when I touch the system here, it seems to change something instantaneously there. Other people call it quantum holism. It's very important, you are going to see why. Quantum holism consists of saying, look, when you have a pair of entangled photons, the property of the pair is more than the reunion, than the sum of the property of the first one and of the second one. There is more in the pair than in the sum of the individual property. Why is it important? Because it's a key of quantum computing. So quality quantum holism is not only philosophic words. It's understanding a very important concept. Entanglement means more. More in the entangled system. Okay. By the way, in case you want to try to build a faster than light radio, I can demonstrate why you cannot send a utilizable signal faster than light. Okay. New quantum revolution, quantum information, quantum cryptography, quantum computing, a few words about it, if Chairman permits. It took a long time for entanglement to be recognized as a revolutionary context. In the 60s, in Lecture of Physics, you know this book, Feynman told us that wave-particle duality for a single particle is the only mystery of quantum mechanics, okay? He writes, we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics, in reality contains the only mystery. And in the same volume, he says that if you analyze the EPR problem, the ones that I described along these lines, then there is no problem. He did not know of Bell's theorem in 60. 20 years later, after understanding Bell's theorem and after hearing about the results of the experiments, okay, Feynman changed his mind. And this is a citation of Feynman in 82, in this paper, which, by the way, well, I will tell you. We always abandon